Hello, so welcome to this video. So in this video we're going to be following on from the last video we looked at on linear algebra. So in the last video we talked about rotation matrices and used this to develop the idea of matrix multiplication, and we talked at the end about the identity matrix, which is a special kind of matrix. And we'll be using the identity matrix a fair bit in this video to talk about not matrices which cause vectors to rotate, but matrices which can stretch or squish vectors. And matrices which do this are related to the vectors they squish or squeeze by what is called the eigenvalue equation. And the eigenvalue equation has application to many things. One example is coupled oscillators. So if we think about having masses connected by springs, then the motion of the masses is actually governed by what ends up reducing down to an eigenvalue equation. That's what Newton's laws reduce down to for such a system. And this is important insight because we can think of a solid as being made up of atoms which are held together by very stiff forces, and we can, by very strong forces, but we can model these very strong forces as very stiff springs. So we can think of kind of atoms in a solid as kind of harmonic oscillators coupled together. And harmonic oscillation is the kind of motion that a mass does when connected to a spring, but when we have masses connected to multiple springs and springs connected to multiple masses, we have something called a kind of coupled system. It's coupled because the motion of one mass is going to affect the motion of another mass, and the motion of that mass is going to be affected by the motion of the first mass. Because as each mass moves, the spring it's attached to is being stretched or squished, which will affect the motion of other masses connected to that spring. And therefore, if we're interested in how atoms in a solid vibrate, and this relates to how heat travels through a solid, also acoustics, so how sound travels through a solid, then one is interested in the eigenvalue equation. So if you love musical instruments, if you love solid state physics, the eigenvalue equation is of use to you. Also, the eigenvalue equation is very important if we're considering making measurements of quantum systems. And we'll be talking about how the time-independent Schrödinger equation is an example of an eigenvalue equation in a little bit once we've introduced exactly what the eigenvalue equation looks like. So for this video, we'll be going through the eigenvalue equation, talking about applications of it, how to solve the eigenvalue equation, and then we'll come on to, at the end, the chicken or the egg question. So does the matrix or the eigenvalues come first? But that's kind of where we're heading in this video. And then in the next video, we'll probably move on to, something more to do with vectors, because the last video and this video has been a lot with matrices. So now we've had a brief introduction to what the eigenvalue equation is, let's be a bit more specific about it. So in the last video, we looked at matrices which can cause a vector to rotate, and rotation is mathematically described by changing the ratio of the components of the vector. But not all matrices will do this to a given vector. So for an example of a matrix which is unaffected by rotation, an example of a vector which is unaffected by rotation is essentially the zero vector, so a vector where all its components are zero. And it's unaffected by rotation because if we think we multiply this by the rotation matrix, we're going to end up with a vector where all its components are zero. So the rotation matrix can't rotate this vector. Now this kind of physically makes sense because this vector is a vector that starts from the origin and ends up at the origin because the vector has a component of 0 horizontally and component of 0 vertically. So in other words, the end and start of the vector both lie at the origin of our coordinate system. So really this vector is in truth just the origin of our coordinate system, and if you try to rotate a point centered at the origin of a coordinate system, it's still going to lie at the origin of the coordinate system. So it kind of makes sense that the zero vector is unaffected by rotation matrices. But this is a fairly trivial matter in that because of how we define vectors, it's fairly obvious that the zero vector will not rotate, if you like, when we use a rotation matrix. However, we can think of less trivial cases and go, well, if we have a matrix, what are non-trivial vectors that matrix won't rotate but will stretch or squish? In other words, what are the non-trivial eigenvectors of the matrix? So if we think of a general matrix A, and we also think of the matrix causing certain vectors, which we call eigenvectors, to squish or stretch, but not rotate. In other words, A doesn't really change the ratio of the components of the vector. Then we can say that when we act A on our eigenvector, the eigenvector is just squished or stretched by a scale factor j. Now j is just a number telling us how much the vector has been stretched by. So if j is 2, then the vector has become twice as long. If j is 4, the vector has become 4 times as long. But it's worth saying j doesn't have to be a whole number. In fact, j can even be negative, and when it's negative, it's saying that we're also flipping the vector. So j is going to be a real number, but it doesn't have to be a whole number, and it doesn't have to be positive. So if we were to write that formally, if we say x with an arrow over it is our eigenvector, then if it's an eigenvector of matrix A, then by definition A times x is just j times x. And this is the eigenvalue equation. It's called the eigenvalue equation because we call j the eigenvalue. Now, if we think of it geometrically, it's telling us how much we squish or stretch a vector. When we apply the eigenvalue to physical systems, it has much more specific meaning for that kind of system. But we'll come on to that soon, but this is a general overview for this slide of the eigenvalue equation, so we're keeping it fairly general. Now, the word Eigen is a German word. And it's a German word because, I mean, a lot of the great early quantum physicists lived in Germany. Um, and matrix algebra, and an example of matrix algebra, or linear algebra generally, is the eigenvalue equation, was really developed to talk about quantum mechanics, a particular form of quantum mechanics developed by Heisenberg called matrix mechanics. Um, and so linear algebra really was kind of fueled by quantum mechanics, hence a lot of jargon in linear algebra, particularly relating to matrices, use German words. So Eigen is the German word which means self or own, so something that is referring to itself. And as a prelude to where we're going in quantum mechanics, for every kind of observable, so for every quantity that relates to the state of a system, so that could be momentum, that could be the kinetic energy, there is an associated matrix, and the relationship between the matrix that describes the observable and the values that that observable can take on for the particular system is given by the eigenvalue equation. So essentially the matrix is referring to the observable itself, hence the idea of eigen. Now that was a bit abstract, but I have other videos talking about matrices in quantum mechanics. So I'll leave the detail for those videos, although we will talk a bit more about the eigenvalue equation in relation to quantum mechanics in a little bit, perhaps even on the next part of this video. So to keep us motivated when we're going to go through a fair bit of maths in this video with solving the eigenvalue equation, we are now going to talk about some applications of it. Particularly for this channel, which has a focus on modern physics, so principally quantum mechanics and relativity, one good example of an eigenvalue equation is one in quantum mechanics for this channel. And the Schrödinger equation can actually take the form of an eigenvalue equation. So the Schrödinger equation is a fairly abstract thing, but in its time-dependent form, there's this matrix called the Hamiltonian, and the Hamiltonian causes the state of the system, and the state is represented as a vector. The Hamiltonian causes the state of the vector to rotate between classical states. And therefore, in the time-dependent form of Schrödinger's equation, the Hamiltonian can be thought of as a rotation matrix, albeit a rotation matrix in the complex plane, because the vector describing the state of the system is complex. That is, it has real and imaginary components. However, if we're looking at a system where there is no time dependence of the system, so its state doesn't evolve with time, and using Schrödinger's equation, you can actually deduce when this will happen. But for a system that doesn't evolve with time, the Hamiltonian stops telling you about evolution of the system or changing the state. Instead, the Hamiltonian starts acting as a matrix whose eigenvectors are the possible well, if you like, classical states of the system. Well, I say classical states, really the possible states of the system. And E is the eigenvalue telling you the energy associated with that particular state. And because we're dealing with time-independent states, it would be states which are classical, at least in terms of having well-defined energy. So for a lot of systems, for example, if you've got an electron that's kind of trapped in a wire, it's governed by the Schrödinger equation, but in the time-independent form, and therefore when you're solving it, and therefore working out the properties of the electron in the wire, you're solving the eigenvalue equation, and you essentially are trying to get the possible states, so the eigenvectors associated with the electron trapped in the wire, and also the possible energies associated with those states. And it's actually this idea that you represent a physical observable as a matrix and then talk about the values for that observable as eigenvalues of that matrix. For example, you say the observable representing energy is the Hamiltonian, and its eigenvalues are the possible energies of the particle. That actually causes there to be only a certain number of possible values for that physical observable. Because if we take a matrix will have a discrete set of eigenvalues. And therefore, by using this eigenvalue equation, we are quantizing physical observables. We are making sure that particles can only take on particular values for physical observables, and physical observables, like energy, stop being continuous. So, for example, an electron trapped in a wire can only have energy out of a discrete set of energies that is viably possible for it. And that's one way where quantum mechanics is different from classical physics, because in classical physics, energy isn't quantized. You know, an electron in a wire can take on any energy it would like in classical physics. And quantization becomes more and more evident the tighter you confine the electron, which is one reason why quantum mechanics is really only prevalent over really tiny distances. So that's kind of an introduction to why we would use the eigenvalue in the context of quantum mechanics. But it does also have applications in classical physics, even though in classical physics, physical observables like energy remain continuous. But we mentioned at the start of the video a particular application. And that application is if we've got coupled harmonic oscillators. So if we've got coupled harmonic oscillators, we can use Newton's laws to work out an equation of motion for the system. And the equation of motion turns out to have the form of an eigenvalue equation. Now, M is our matrix that has the associated eigenvalues and eigenvectors. And M is a matrix which ends up referring to how stiff the springs are that connect the masses. The stiffness of the spring is usually described by a constant called Hooke's constant, which has the symbol K. And So M is a matrix which depends upon K. And different springs can have different values of K if you like. X is a vector, and this vector, the components of this vector is the amplitude of the oscillation of the masses. So how far, each component refers to how far a particular mass can move away from its equilibrium position. And then we have an omega term. An omega tells us about the angular frequency of the harmonic oscillators. So it's talking about how quickly they're oscillating. And so, your minus omega squared here is your eigenvalue, which tells us about how quickly the oscillations are occurring, and x is your eigenvector. And in this kind of model, you're interested in both. You're interested in the eigenvector because that tells you how large the displacement of the masses can get, the amplitude of the oscillations, and omega tells you something about how quickly the oscillations are occurring. And as we said, because we can model atoms in a solid as essentially masses connected by springs, this kind of eigenvalue approach is usually helpful if we're looking at kind of vibrations of atoms in a solid, and therefore things like how solids conduct heat, how sound travels through solids. And an interesting point where quantum mechanics and solid state physics meet, particularly given what we said here, is where one thinks of the kind of, because in quantum mechanics energy is quantized, also the vibrational energy is quantized. And therefore we can think of the coupled harmonic oscillation as being described by particles that carry, if you like, this vibrational energy, and they're particles because the vibrational energy is quantized. And these particles are called phonons. Importantly, not photons, they're called phonons. And they're called pseudo-particles because they don't actually exist in the standard model of particle physics, but they're useful for describing how sound and heat travels through a solid. So that's why the eigenvalue equation is important. Now we're going to go on to solving it. It's worth saying this is going to get quite mathematical, but hopefully, even if you're not so interested in the maths, at least this part of the video has been helpful in explaining why we care so much about the eigenvalue equation, so much so that there's many videos, including now this one, on this single type of equation, which at first looks so extremely specific. So if we're solving the eigenvalue equation, we essentially would like to make it simpler. Now, a way to make it simpler, or a way to make most equations simpler, is to factorize. That is to bring terms to one side of the equation that have something in common. If we look at the eigenvalue equation, both sides contain our eigenvector x, so we might like to factorize out x and bring everything to one side, leaving us with an expression of a minus j, all multiplied by x gives us 0. And this seems to work in terms of factorization. However, there's an immediate problem with interpreting what this means and trying to solve it. And that's that A is a matrix, J is a eigenvalue, so it's a number. For all purposes, it's always going to be a real number. So what does A minus J mean? What do we get when we take away a number from a matrix? it's really not very well defined, and so we have to in some way get around this problem, and we actually do this through use of the identity matrix, as we'll look to in a bit. And we use the identity matrix because it gives us a way to turn our number j into something into its matrix equivalent. And there's already hints with what we said in the previous video that we might want to use the identity matrix to do this, because we said the identity matrix is the matrix equivalent to the number 1. So the identity matrix is our first and primary matrix, which is a matrix version of a particular number. So we might already infer that, well, if we have a matrix version of 1 and that's the identity matrix, we should somehow be able to use the identity matrix to get a matrix version of the number j. So that's what we're going to look at next, getting a matrix version of the number j, and then that will allow us to make sense of the term we have in our brackets where we've factored out our eigenvector. So now this bit of the video is going to be probably the most mathematically technical, where we find a matrix equivalent to a number. But we need to do this to solve the eigenvalue equation. So as we've said, we have a bit of difficulty at first interpreting what a matrix takeaway number is, so we need to convert the number into a matrix form, and we might initially not know what to do. Well, we look at a matrix that we've already talked about, which is the equivalent to a number, and that's the identity matrix. And we would recall that the identity matrix is the equivalent to the number 1. So if we're thinking of representing j as a matrix, we can go, well, however we get to j using number 1 will be similar to how we get to the matrix version of j using the identity matrix. So if we think about a number that j could be, hypothetically, like let's take j as 2. So we can get 2 by adding 1 and 1. And providing j is a whole number, we can get j by just repeatedly adding 1. So we might say, well, if j is a whole number, then the matrix equivalent of j is just going to be given by adding the identity matrix to itself repeatedly, in direct analogy to how we construct a large whole number using the number 1. And then we have to ask the question, well, how do we add matrices together? Because it's worth saying, although perhaps you may have seen how we add matrices together before, you may not have. Also, even if you have, we haven't in this series of videos really talked about how we add matrices together. Well, to work out a sensible way to add matrices together, we can think back to particular kinds of matrices which we already know how we add them together. An example is a vector, because a vector with n components is just a n by 1 matrix, as we talked about in the last video. So by extending how we add components together when we're adding vectors to get our new vector, we can generalize that to say how we would add matrices together. So if we've got two vectors A and B and we add them together and we get a vector C, then in terms of how vectors add together, we know, and one can show relatively easily geometrically, that the components of C is just given by adding the components of A and B together. For example, let's say A and B, just moving the camera, and it wobbled a bit. That will have to do. So let's say A and B are vectors, each with 2 components. So they're living on the complex plane. Then if we add them together to get a new vector C, then the horizontal component of C is just the horizontal component of A adds the horizontal component of B, and also the vertical component of C is just the vertical component of A adds the vertical component of B. So we get a matrix by adding the components of the other matrices together, where the components we add together are components in the same place as the component we're trying to calculate. So for example, with matrices, to get the top number of, well, say with vectors, to get the top number in our new vector, we add together the top numbers in the vectors, we bring them together. Just going to quickly power this in. Well, actually, I'll wait to the next slide. So hopefully my laptop doesn't run out of power. But so to put what we said formally, if we have a matrix C, then Cij, so the component of C that is in the ith row and jth column, is given by adding Aij and Bij together. And so if we apply this rule for how we add matrices together to our definition for the matrix equivalent of J, then we can see that in the case where J is a whole number, our matrix equivalent of J is just a diagonal matrix where all the terms in the leading diagonal is equal to J. Or in other words, Jij is just our number J multiplied by the ijth component of our identity matrix. It's worth saying often people are fairly relaxed with notation and they'll write something like J times A, even where their J is a number. What they really mean is the matrix equivalent of what they really mean is the matrix equivalent of J multiplied by A by a matrix multiplication. So this has been how we get the matrix version of J, where J is a whole number. But if J isn't a whole number, then we just extend this idea and we just say, well, for any number J, any real number J at least, the matrix equivalent of J is just a diagonal matrix where all the diagonal components are equal to J. No matter if J is positive, negative, a fraction, an irrational number, whatever. So now we have a matrix equivalent to J, we can now make sense of what A minus J would be. We just replace the J as an which is our eigenvalue, with its matrix equivalent. And that will allow us to then make sense of the term we had in brackets, and thus help us immensely in solving the eigenvalue equation. So we're now going to solve the eigenvalue equation, and we're going to introduce an operation that we can apply to matrices to do this, called a determinant. And I've got a pink parallelogram here, which has a visual, well, shows geometrically a way to think about the determinant of a 2 by 2 matrix. and in fact matrices generally, are square matrices. But we'll come on to that in a bit. For now, we'll recall that we'll try to solve our eigenvalue equation, and we made real progress by firstly factorising, but then noting to make sense of the term in the brackets, we need to replace J with its matrix equivalent, and we deduced that the matrix equivalent of J is just, well, has components which is equal to the eigenvalue J multiplied by the component of the identity matrix. And so we rewrite, if you like, our factorised version of the eigenvalue equation as A minus J, but now J is the matrix equivalent, multiplied with the eigenvector x is equal to 0. And to make things simple, we can actually, because A is a matrix and now J is a matrix, A minus J is going to give me another matrix. Because we saw adding matrices together gives me a matrix, so logically subtracting the inverse of addition should also give me a matrix. So we can call the matrix we get by doing A minus matrix J. We can call the matrix we get just another matrix C. And it turns out we'll use a particular function of C, if you like, or the components of C, called the determinant of our matrix C. And we get there by noting that if we're going to solve our eigenvalue equation, we now reduce our eigenvalue equation to the statement that a matrix C times our eigenvector equals 0, where C is equal to A minus our matrix J. And if we think about the rules for how we multiply matrices together, and it's worth saying here this is going to be a bit confusing because when we talked about how we multiply matrices together, we use C to represent the output of multiplying matrices A and B. But if we have matrices A and B and they multiply together to give us C, then the components of A, B and C are related by the top equation in the blue box. And if we now apply this to our eigenvalue equation, well, as we said, our eigenvalue equation reduces to matrix C times our eigenvector, which we can think of as another matrix X, is equal to 0, and writing that explicitly in terms of matrix multiplication, we have 0 is the sum over K of Cik xk1. And if you're not sure what exactly this matrix expression for matrix multiplication means, I would heavily recommend checking out the video I did previously on matrix multiplication, which doesn't assume any knowledge of matrices, but does explain where this formula comes from and how this kind of equation works. Although here we're applying matrix multiplication to the eigenvalue equation. So, in other words, our eigenvalue equation has now reduced really to solving this kind of summation expression equaling 0, where the summation relates the components of our matrix C with the vector components of X. And if you're going to write out explicitly, you know, using if we think of X as having two components and therefore C being a 2 by 2 matrix, and we write out explicitly how the components are going to have to relate to each other based on our equation, then we end up with essentially a pair of simultaneous equations. And they're simultaneous because they both contain commonly both components of x, so x11 and x21. And you can use kind of just fairly standard algebra, although it gets quite lengthy, to condense those simultaneous equations down into the statement that the product of the diagonal terms in our 2x2 matrix take away the product of our off-diagonal terms will have to equal 0. And we call and we say when we're for a 2x2 matrix at least, when we're taking the product of the diagonal components and subtracting the product of the off-diagonal components, we say we're taking the determinant of our 2x2 matrix. So one way of writing this is just det, which stands for determinant of C equals 0. Now you might wonder what the determinant means. I would probably have done a video on it, however there are plenty of really amazing videos, some with super cool animations, which I can't really contend with. So I'll leave a full video on determinants to kind of to other YouTubers. However, I will put a link below to at least one video on determinants for those who would like to get a understanding for what the determinant of a matrix actually means. But I've got a picture that in some way summarises it. So if we imagine a matrix as having components, A is our component on the first row, first column. Then also on the top we've got B, and then down below we've got C, and then our last diagonal component at the very corner is D. And let's imagine this is our 2x2 matrix. Then it turns out that the determinant of the matrix is equivalent to the area of the parallelogram, where the corners of the parallelogram are given as they are here on the screen. So the determinant of a matrix is really referring to area. And there's plenty of videos that go into more detail, but for our purpose, really the determinant, we use the idea of the determinant because it's just something that the eigenvalue equation boils down to. When you're solving the eigenvalue equation, it really reduces to finding the determinant of our matrix, so the determinant of C, which as a reminder is, C is defined to be our matrix minus the matrix version of its eigenvalues, of A's eigenvalues. So we've now really covered all the maths and we can put it all together. So really summarising what we had on the last slide, essentially our kind of eigenvalue equation reduces to finding the determinant of a matrix C, and because C is defined to be A minus the matrix version of the eigenvalue J, finding the determinants of C reduces down to actually solving a quadratic in terms of J, our eigenvalue that we're trying to find. And it's a quadratic in terms of J because if we're finding the eigenvalue eigenvalue or the eigenvectors, we can take it for granted we know A, so we know all of the components of A. So, A11, A22, A21, and A12 are all going to be known numbers, so they're not unknowns. So really we've got an expression where we've got bunches of numbers, but we've got two terms in our brackets containing j, which is the thing we're trying to find. So we have, if we multiply out the brackets, we have a quadratic in terms of j. So, something that seems completely unrelated. So quadratic formula, which you might think of as, trying to find, for example, where a parabola crosses the x-axis. That kind of maths is bizarrely useful in the eigenvalue equation, which seems to have nothing to do with it, providing the matrix we're dealing with A is a 2 by 2 matrix. You can generalize this to talk about other square matrices, providing you can talk about the determinants of the matrix, you can solve the eigenvalue equation. So you can solve the eigenvalue equation for any square matrix, but we're focused on this video for 2 by 2 matrices. And therefore providing A is a 2 by 2 matrix, then finding J just reduces down to solving a quadratic formula. And solving a quadratic formula is fairly standard, so I'm not going to go through that in a fair amount of depth because you would have done that in high school. It's worth saying it's a long formula. You might need a bit of a refresher on solving quadratics, but it's not really worth spending a very long time on this video talking about it when our main focus will be, on the eigenvalue equation. However, I would like to go through an example, because solving quadratics might be unfamiliar, and also thinking of the eigenvalue equations reducing down to a quadratic and solving the quadratic actually tells us a lot about the matrix we're trying to find the eigenvalue or eigenvectors of. Particularly, for example, the identity matrix. So let's have a go at finding the eigenvalues of our identity matrix. And again, we're taking for this video all the matrices A to be 2 by 2 matrices. So our identity matrix is going to be 2 by 2 identity matrix. And using the recipe we have for finding the eigenvalues of this matrix, we end up ultimately having a quadratic in J that we can factorize, and then we get a repeated solution. It's repeated because both brackets that we end up with refer to J having this particular value, and this particular value is 1. So, usually if we have 2 by 2 matrices, we end up having a quadratic in J. J will have 2 distinct values it can take on, but for our identity matrix, its eigenvalue, well, it only has one eigenvalue, and that's 1. And remember we said J as a number tells us how much we're stretching or squishing a vector. So what this tells us is whatever the eigenvectors of our identity matrix will be, so whatever vectors the identity matrix won't rotate but will stretch or squish, the identity matrix will actually just stretch or squish it by a scale factor of 1. So in other words, it won't change the length of the vector at all, because the length of the new vector will be just 1 times the length of the old vector. So as our eigenvectors by definition are not being rotated by our matrix that they're eigenvectors of, and also for the identity matrix, the eigenvectors aren't being stretched or squished at all, what that tells us is the identity matrix is actually changing its eigenvectors at all. But this is exactly what we would expect, because remember, we defined the identity matrix to be a matrix such that when we multiply any matrix, and that includes a vector, by it, we get back the original matrix. So if we're trying to multiply our eigenvector by the identity matrix, we should get back the original eigenvector. It shouldn't, its length shouldn't change, or it shouldn't change at all, in fact. So the idea that the eigenvalue is 1 for the identity matrix is actually completely coherent with what we've defined the identity matrix to be. So we talked about finding eigenvalues. The last thing to then talk about is finding eigenvectors. So if you want to find the eigenvectors, and as we mentioned before, the eigenvectors have just as much physical significance as the eigenvalues. So you're often interested in finding both. The way you do this is, so firstly, when you solve the eigenvalue equation, you find the eigenvalues. But once you've got the eigenvalues, well, in our eigenvalue equation, we've got our matrix, which we know because we're given it. We know our matrix A and all of its components. We've also worked out now the eigenvalues J, and therefore there's only one unknown in our equation, the eigenvector x. And so we can very easily now find what x is. So finding x is quite straightforward once you've got your eigenvalue, because everything is then else is known. And what you would traditionally do is you would use matrix multiplication to explicitly work out if we represent x as a vector with two components. If its components cubic general is x and y, you would use matrix algebra to work out what A times x would be in terms of x and y, and then because of your equation that must equal J times your components of x. So you'll have Jx at the top and Jy at the bottom, and then by the equality you'll then end up with one equation for how the top components of x relate to one equation for the bottom components, and then it reduces to a simultaneous equation you could solve. Now I've gone through that rather vaguely, but I would encourage you to have a go at picking a matrix, finding the eigenvalues like we have done before, and then having a go at finding the eigenvectors. But we're going to go back to our identity matrix, and again the eigenvectors is going to be very informative as to the properties of our identity matrix. So as we've said, if we want to find the eigenvectors, we just replace our vector x with the kind of generic components, and then we can use matrix algebra and simultaneous equations after that to work out explicitly how x and, well, how the components of our vector x relate, and thus the eigenvectors of our matrix. So replacing our vector x with generic components x and y, we have this expression for the eigenvectors of our identity matrix, and the 1 here is our eigenvalue, and we've shown just a moment ago that the eigenvalue of our identity matrix is 1. However, note that this equation, by the way we define matrix algebra, will actually work for all values of x and y. So we can pick any ratio of x and y we like, and this equation will work. So what that ends up saying is that essentially, very specially for the identity matrix, all vectors we can think of are going to be eigenvectors of the identity matrix. Because for any value x and y we pick, a vector with components x and y will be an eigenvector of our 2x2 identity matrix. And so we can actually define the identity matrix fairly abstractly. So we've said essentially any vector with two components, so a 2x1 matrix, will be an eigenvector of our 2x2 identity matrix, but we can generalize this to a vector with n components, so not necessarily 2, and we can say that the identity matrix is a n by n matrix such that any n by 1 matrix, i.e. a vector with n components, is going to be an eigenvector of the identity matrix. And so you can actually define the identity matrix with regards to the idea of eigenvectors. And this makes sense because we've said again that the identity matrix should leave any vector unchanged, so any vector should be an eigenvector of it. So this idea of eigenvalues and eigenvectors can be abstract, but relates very neatly to what we've done, and as well as the identity matrix being useful in solving the eigenvalue equation, it helps us make physical sense of what these eigenvectors and eigenvalues really are in a more concrete way. So, as we mentioned, when solving the eigenvalue equation, we're essentially relating the eigenvalues and eigenvectors to a matrix. So one might ask kind of what comes first, the matrix or the eigenvalues and eigenvectors? Because if we define the eigenvalues and eigenvectors, then we have in a manner defined the matrix, and also if we give the matrix, then that dictates the eigenvalues and eigenvectors. So what parts of our kind of equation, our eigenvalue equation, actually come first? And there's a real right answer to this, because they're so related. You could argue it either way, but if we think of physical systems, we get something which is a lot easier to say what comes first. So in the context of quantum mechanics, as we said, if we're considering a system that doesn't change with time, so has a state that isn't time dependent, or using technical jargon we say has a stationary state, then the eigenvector represents the state of the system, or a possible classical state of the system anyway, at least classical in terms of that physical observable. The eigenvalue represents the value we would measure for that physical observable if we found that system in that classical state, and the matrix represents measuring that physical observable. And so usually, because a matrix is just a representation of a physical observable, it doesn't really make much sense to start with a matrix representation, because we wouldn't know how to represent a physical observable as a matrix most of the time, at least immediately. So instead, it's a lot more physical and natural to think about, well, what state is the system in, and what values can I measure for its viable classical states that I can find it in. And therefore, physically, the idea of the eigenvalue and eigenvector is very well defined, and we actually use them to construct the matrix that represents the measurement of our observable that the state corresponds to. So, for example, if we're talking about the ith classical state, then if we add the Hamiltonian on the ith classical state, we'll get the energy of the ith classical state multiplied by that classical state, where that classical state is represented as a vector. So really, in terms of quantum mechanics, it's the eigenvalues and eigenvectors which come first, and they define the components of the matrix. And actually, if you move on to look at the kind of matrix formulation of quantum mechanics, you'll see explicitly how we define the components of an operator that reflects a physical observable in terms of thinking about the eigenvalues and eigenvectors. And it's worth saying we can pick different eigenvectors. That is, if we've got a system where it can have different classical states, then that same physical observable will be represented with a matrix with different components. So whenever we describe a physical observable in quantum mechanics, we always say we are representing that observable in a particular basis, and the basis refers to the eigenvectors we are building we are working out the components of our matrix from. Now that's fairly abstract, but it's just worth talking about in terms of what comes first. But mathematically, it's all tied together, and in terms of pure maths, really, the eigenvalues and eigenvectors and the matrices they correspond to are also entangled, but you can't really say which thing you start with.